Hi, we're going to start chapter 8. It's the one sample t-test. And this is going to be very similar to the z-test that you've already learned. There's just going to be some subtle nuances. So at this point in um, Intro to Statistics, a lot of this will become repetitious. So it's helpful because once you get chapter 7 down, chapter 8 is very similar and it continues to be similar. The only thing that changes per se is the calculations and why we do the calculations. That's really the only major nuance differences. So let's take a look at the t statistic. So when we use the t statistic rather than the z statistic, it is because we do not have a population variance. So a t-statistic does the same thing as the z-test, except it basically describes the number of standard deviations that the sample deviates from the population as the null is stated. So the null, meaning the population mean that's given, we're going to see how many standard deviations does that sample deviate from that. And that's what the t-statistic tells us. Um, but we use this specifically when we have a population mean, but we don't have a variance. So typically in social behavioral science, we actually don't know the population variance is what we're dealing with is usually some hypothetical population mean or just a population mean in general where we don't have the population variance. So is what we do is we have to take the sample variance and estimate what the population variance would be to calculate that standard error. And then it's called the estimated standard error. So let's take a look at that. So previously, as you can see, when we were using the z-test, we had right here that population standard deviation. And so our notation was SEM for the standard error of the mean. Now, when we're using the t statistic, our notation changes. It's lowercase s subtext m, and now we are using the sample standard deviation in that numerator. And so that's the major change. And now it's called the estimated standard error. And so our population variance or population standard deviation is unknown. So we use the sample standard deviation as an estimate of that. So the t statistic, the calculation for that now, it looks exactly like it did with the z-test, except for now we're looking for a t obtained. And now we have the sample mean minus the population mean because we have a known population mean, but now we're using that estimated standard error, the S subtext M, which is the standard deviation of the sample divided by the square root of n to calculate our t statistic. And that is that test statistic, the t obtained instead of the z obtained. It is the major difference with this. So when we're calculating the t statistic, we are going to be using now the t distribution instead of the unit normal distribution or the sampling means distribution. And there is a different distribution for um, every sample size. Every sample size or every degrees of freedom has its own distribution to compare things to. So as the sample size increases, just like we talked about with the central limit theorem, as the sample size increases or as the degrees of freedom increases, the t distribution becomes closer to a normal distribution. And there is a different t distribution for every sample size. So you'll notice we're going to be using a different table to find the critical boundaries now. So you can set your unit normal table aside and discontinue using that. And now you will be using the t distribution. Then that comes immediately after the unit normal distribution in your textbook. It starts at it's at page 297. It's called the t distribution table. And it's only one page. And it goes, it's based on degrees of freedom. So we're going to learn how to use that. And that's what you'll be using to find those critical values now. So here's kind of an example of what you'll notice from the textbook. This has some highlighting though. Um, Now you're going to need to have your alpha level to set that criteria. So alpha level being either 0.05 or 0.01. You're going to need your sample size so that you can obtain your degrees of freedom. And then you'll need to know whether it's a one-tail test or two-tail test. So as you can see with this table, it looks very different. You don't just have one distribution, you have multiple different distributions. So let's say if we had a sample size of 5, okay? If we have a sample size of 5, so n equals 5, our degrees of freedom would be n minus 1, which would be 5 minus 1. So our degrees of freedom would equal 4, right? So we're going to look here at 4. Here's our degrees of freedom. But now we need to know, okay, what's the alpha level? And is it one tail or two tail? So let's say if it's two tail and 0.05, you'll notice right here it says proportion and tails combined. So you no longer have to split your alpha level. You're going to look at 0.05. Right here is the 0.05. Hopefully you can see that, that 0.05. And we're going to find it's under with 4 corresponding right here, 2.776. So our T critical value equals positive and negative 2.776 because it's a two-tail test. So it would be on both ends of the distribution. If it's 0.01 two tails, you're going to look in this column, this last column right here. And so that would be an alpha level or a critical value of 4.604 if you were using alpha 0.05. If you're using one tail, you're going to use this section up here to distinguish which columns you're using. So here's the 0.05 for one tail, and here's the 0.01 for one tail, that third column over. So you no longer have to split your alpha levels. The table is going to do it for you. So it's going to be a different critical value depending upon sample size and degrees of freedom. So probably the hardest thing is getting used to the tables. Just keep practicing that, and you'll have opportunities to practice that. So here's an example. Here's another example. Say we have a sample of 15 students. Okay, so 15 is our sample size. We're going to use 0.05 to tell. So you're going to get your degrees of freedom. Degrees of freedom is 14. Here's our degree of freedom column right here, 14. We're going to find 0.05 to tell. So we're going to look in the to tell column section, which is right here. And if you'll notice, it's 2.145. Sorry, that was crooked. But it's positive and negative because it's both ends of the tell, recall? So just as simple as that. Degrees of freedom, find the appropriate column, and then locate that critical value. So before you even start testing a hypothesis using the t-test, there are some assumptions that you need to be aware of. And basically, assumptions are something that we want to make sure that we align with these assumptions that we meet to assure that the results are valid. If you don't meet these assumptions, your results are more than likely problematic. They're hindered in some way. Either you aren't getting significance because you didn't meet assumptions or something to that extent. So the first assumption with the one sample t-test is normality. So the population that you take the sample from must be normal, which means, a symmetrical distribution, a peak in the middle, tails on the end. So you either have to assure that the population is normal, the population the sample is taken from, or you use a sample size of 30 or larger. So typically, if you're doing research, that's why you'll hear research saying, make sure you get a large sample size, at least 30 people in each group. That's so that you can assure you've met normality. Another one is independence. So basically, every outcome is independent of the other. So one outcome does not influence another outcome. So let's say we're running in a race. My time at the end of that race is not influenced at all by anyone else, any other time, or from about influenced by my previous times. It's just that race, that time. It's not influenced by others, and it's not influenced by prior races, that score, that outcome. So independence has to be assured. So these are two simple assumptions that need to be met for us to make sure that our um, results are valid results. So another thing, if you remember, we go through the normal steps. Step one is state the hypotheses. Step two is set the criteria. Step three is calculate the test statistics, collect the data. We now will be calculating effect size with the estimated Cohen's d or eta squared. So estimated Cohen's d looks very similar to what you've done previously, but now it's called estimated because we're using that sample standard deviation right here rather than the population standard deviation. So it's the same calculation, except for you use the sample standard deviation in the denominator. And it's an estimate. And in reality, this D here has like a little hat over it to tell us, that it's estimated, but I don't require the little hat. It's not a big deal. We should know that it's estimated. And is what that tells us is the number of standard deviations that the score shifted above or below the mean as stated by the null hypothesis. So, and this is due to the treatment effect and it's absent of the sample size. So the sample size won't influence it. The second effect size, so you'll really choose which one to calculate. You don't have to do both, but you'll choose which one. I typically use Cohen's d because it is not influenced by potential errors in calculations as much as eta squared, but you do need to know what each of them are measuring. So estimated Cohen's d tells us the magnitude of the treatment effect, so how much your mean shifted. Eta squared measures the proportion of variance in the dependent variable that is accounted for by the independent variable. So how much is that dependent variable actually being influenced by the independent variable? And it is a proportion. So again, it's only between 0 and 1. It can't be larger than 1, where estimated Cohen's d can be. So with eta squared, it's, as you could see, eta, it's like a little symbol, like an N, but with a long little tail, squared. And it, because it's squared, obviously it can only be positive. Eta squared can only be positive. It is your t obtained squared divided by the t obtained squared plus degrees of freedom. So it's that obtained test statistic, not your critical value. This is where you should write this in your notes in bold. Your obtained test statistic, not the critical value. That is probably the biggest mistake I see. And when you calculate these, I'd put these in parentheses because otherwise it'll be t squared divided by t squared, and that's 1 plus your degrees of freedom, and that's a problem. So you want to make sure you put that in parentheses in your calculator. So another thing that you'll be calculating with the one sample t-test is a confidence interval. You're actually going to be calculating a confidence interval with all of your t-tests. So you're going to learn 3 different t-tests this semester. You'll have the one sample t-test, which we're learning now. You'll have the independent measures t-test, which is chapter 9. And then you'll have the paired samples t-test, which is chapter 10 with the textbook that is currently being used. A confidence interval is a range of values. So the key here is that word range. When you have a range, that means there's 2 values, a lower end and an upper end, where the population parameter, basically the population mean, would fall when the null hypothesis is true. And this is estimating what we would see in the population. It's always calculated to include within that APA result, just like an effect size is always calculated to include in the APA result. And so is what it does is it estimates the location of the lower boundary for the population mean and the upper boundary of the population mean. So here's what it looks like. So this is like an estimate of the mean. So you're going to use the sample mean plus and minus t times the estimated standard error. Now the t here, this one is the critical value. So in effect size with the eta squared, it's the obtained test statistic. This t is a critical value, and it is always two-tailed critical value. So even if your original test, like when you look up that criteria is one tail, when you calculate your confidence interval, you must calculate it as a two-tailed. So because that's a range. You can't have a range with only one number. And if it was one tail, it would only be one number. So you have to have two. You have to have the upper and lower. So that means you would go back into that t-distribution table and locate the critical value using the degrees of freedom for a two-tailed test. So this is another one where you might want to, at this portion of it, write in big, bold letters, a critical value for two-tail only. Two-tail test, always a two-tail for the confidence interval. So 4 steps are the same. It's always going to be the same. You state your hypotheses first. In this class, you really only need, at this point forward, I'm only requiring you to state the alternative hypothesis with the notation. So that alternative is H of 1, and that's your prediction. Should include your independent variable, your dependent variable, and whether there's a direction or not. You're going to set your criteria for the decision. So that means you go beyond just stating that alpha level, you have to provide me your critical value as well. In this case, it's the T critical value. You collect your data, which often I do that for you, and then you compute that the sample statistics. So that means your T statistic, if I could speak right, your T test, an effect size. So you would choose either Cohen's d or eta squared, and your confidence interval. Then you're going to use that information and you'll make a decision, but you're also going to report your results in APA results. So remember, within that make a decision is also APA result. That is extremely important. So as part of step 4. So here's an example research scenario. So we'll go through the 4 steps together. So it says, according to a national collegiate report, college students spend an average of 17 hours per week studying. Now, here's where you want to be careful, like, because it says a national collegiate report, this average of 17 is a population. So mu equals 17. And you think the students in your local dormitory study significantly different than the general population. Because this just says different, it doesn't say they don't study significantly more or significantly less. You're just saying they're different. That's suggesting a two-tailed test. So you randomly select 18 students from your local dormitory. So that is your sample size. So now we have n equals 18, lowercase n equals 18. Ask them how much they study each day. Your results for the 18 students showed an average study time of 20 hours per week. So those 18 students are a sample. So the study time, the average is 20 hours. So our sample mean, capital M, equals 20. And I've calculated up to the sums of square for you. Sums of square is 724. Now, if you remember, sums of square is what we need to get variance. So if you look here, or standard deviation equals our sums of square over degrees of freedom, all under the square root. Because sums of square divided by degrees of freedom without the square root is the variance. But to get standard deviation, we're going to take the square root of that. So I've done a lot of the math for you. So that sums of square is for you to help calculate those statistics. And it says we're going to use alpha level 0.05. So 0.05, oops, right here. So we're going to start the process. Don't jump ahead and start calculations. Don't jump ahead and set the criteria. The first thing you want to do is state your hypotheses so that you make sure that your hypothesis, your prediction, matches your criteria, which then will help set you up for making a decision and stating your results. So here's our hypotheses. So here's that scenario up top. I have both the null and the alternative here, but on the exam, for chapter 8, 9, and 10, you're only going to need to give me your alternative hypothesis. So that H of 1. And mine is the number of hours that students study in a local dormitory will be significantly different than the general population. So the hours of study, that is the dependent variable. Okay. And where the dormitory is the independent variable. Okay, so you can kind of see what is the independent variable, what's the dependent variable, and significantly different is just you're not saying one way or another whether it's going to increase or decrease or be more or less. So it sets you up automatically for a two-tell test. Step 2 is setting the criteria. So we know it's alpha 0.05. Our sample size was 18, so the degrees of freedom is 17. And you're going to look that up in the t-distribution table. So you're going to look up 0.05 to tell with a degrees of freedom of 17. So you'll look at 17, 0.05 to tells, and you should be finding 2.110. Now, when you write that, you should either have this or you should basically have this set up. I always suggest until you're really, really good at determining whether things are significant, draw the distribution and put your tells in and your critical region so that you know if your test statistic falls in this region or this region is significant. If it falls anywhere in this middle area, it's not significant. It's helpful. Visual tools are helpful. Okay. So let's start calculating that test statistic because we already have, the data's been collected. We just need to pull the data together. So I always create a legend, just like something like this when I have information. So I know what I have to work with and I can just plug and chug at that point. So our test statistic is the sample mean minus the population mean divided by the estimated standard error. So we're going to calculate the standard deviation so that we can get to the standard error. So that sums of squares divided by the degrees of freedom, which is n minus 1. So 724 divided by 17, take the square root, it's 6.52597. And I would keep as many decimals as possible just so that your answer is very accurate. Now you're going to take that standard deviation and calculate your error, as you can see. So standard deviation divided by the square root of n. So 6.52597 divided by the square root of 18. Now, the biggest mistake I see here is people using the degrees of freedom again. This is n, not degrees of freedom. So make sure the only time you should be using degrees of freedom is in your variance equation, which is right here. And that's for sample variance. So if it was population variance, you wouldn't use degrees of freedom. So only in the variance equation do you use degrees of freedom. So this is by 18. So your error is 1.5382. So now we can plug and chug and compute that test statistic. So sample mean minus population mean divided by the error, which is we end up with a test statistic of 1.95. Okay, but we're not done yet in step 3. That's just the first part of step 3. We need to get an effect size, and you can choose which effect size to calculate, but I'm going to walk through both of these with you just so you learn them so you can have that choice. And then there'll be times where you might be asked to calculate both, or there might be times that you at least need to describe what that effect size means. So with Cohen's d, we're going to use that standard deviation, and it's going to be our estimated Cohen's d. So 20 minus 17 divided by that standard deviation, 6.52957, which is 0.46. So is what that means is that that sample mean shifted above the population mean by 0.46 deviations, standard deviations. Okay. And then there's eta squared. Eta squared, again, remember these are the obtained test statistics. So 1.95 squared. If this was a negative, like a negative 1.95, when you put it in your calculator, you might want to drop the negative, because is what happens, unless you put parentheses in a perfect way, it's going to hold the negative, and they shouldn't be. Any squared number should not be negative. So 1.95 squared divided by 1.95 squared plus 17. So remember this, I would make sure this is in parentheses when you're calculating that, so you're not accidentally adding 17 to 1. So your eta squared is 0.18 is what that means. If we convert that to percentage, it means that 18% of the variance in the dependent variable, meaning the 18% of the scores or study hours. Study hours was our dependent variable, can be accounted for by where they live, the dormitory. 18% of those results can be accounted for by which dormitory they live in. Still not done with step 3, unfortunately. Sorry. Now we calculate our confidence interval. So it's that range of values where the population mean is likely to fall if the null is true. So first thing we're going to do is get our critical value for 0.05 2-tel, right? For 2-tel. Because this original test was 2-tel, we can use the same. But if the original test was not 2-tel, if it was 1-tel, we have to go back into our t-distribution table and find the critical value for 2-tel. So our critical value is positive and negative 2.110. Then we're going to calculate our margin of error. The margin of error is just that t critical times the error. So if you remember, like the overall equation was m plus or minus t crit times the estimated standard error. This is basically the margin of error that we're going to add to the mean and subtract from the mean. So 3.2456. Then we're going to get the lower boundary. So our sample mean, just 20, minus that 3.2456, that error. So our lower boundary is 16.75. And then our sample mean plus that error, which is 20 plus 3.2456, because it's sample mean, and the upper is 23.25. So we can be basically 95% confident because the alpha level is 0.05. 0.05 in the tails is 5%. The rest in the middle is 95%. We can be 95% confident that the population mean would fall between 16.75 and 23.25 if the null is true. Okay, that is if the null is true, it would fall within that range. So if you notice, we have the population mean is 17. And if we have 16.75 is over here, and 23.25 is over here, our population mean falls within that in the middle of that. So we're more than likely retaining the null. And then if we compare the absolute values of the test statistic, we can see that as well, because our critical value is 2.110. Our obtained test statistic is 1.95. So if you'll look at our distribution here, we have 2.110. Here's our critical region. We have negative 2.11 over here. Sorry, it's messy. 1.95 it falls like somewhere over here. So it's not significant. It falls within the middle instead of out in the tails. And this population mean falls in between those boundaries. So again, we're retaining the null. We can see that more than likely, you could see that the test was not significant in two different ways now, two very specific ways. So now we made our decision and we can write our results in APA format. So it wasn't significant. So now we just basically regurgitate our null hypothesis. But our format changes a little bit because there's not just one distribution for this test. There's a distribution for every degrees of freedom. We actually need to include our degrees of freedom and as well as our confidence interval, and it should always be in the exact format. So we're going to state basically that the dependent variable was not significantly different, and this should actually say significantly different rather than more different. I think at one point I did it as a one-tail test. It was not significantly different because the test statistic was not in the tails as T, and we're going to report our degrees of freedom that we use to look up our critical value equals 1.95. Now we no longer have p-values because there's a different p-value for every distribution, everything. There's too many p-values. So we know that p is greater than alpha because it wasn't significant. If it was significant, p would be less than. So you just have to know that p is greater than 0.05. There is a supplemental video that says that is determining significance with p, with the p-value. If this is confusing you, I would definitely go in there and watch that video in Canvas so that you can kind of understand how p is related to alpha. So it was not significant, so p is greater than alpha. We state whether it's two-tailed or one-tailed. This one was two-tailed. I reported my Cohen's d, but you would be okay if you reported your eta squared, but I reported Cohen's d. That's the one that I report the most often. And then a 95% confidence interval. So 95% because it was 0.05. If it was 0.01, it would be a 99% confidence interval because 0.01 is 1%. Subtract that from 100%, that's 99%. Alpha of 0.05 is 5%, subtract that from 100%, and that's 95%. CI, and then it's brackets, your lower confidence interval, comma, upper confidence interval, close the bracket, period. It's all one sentence, and that is your APA results for that. So as you know, we talked about power before, and we talked about error. In this case, if I said, what type of error could you have made in your result? You would say, I could have made a type 2 error, right? And my alpha level was too stringent. I would have to make it less stringent. We would never make our alpha level less stringent than 0.05, but that's kind of a rote answer that you would give, a type 2 error because we retained the null, and maybe our alpha level was too stringent, so we would make our alpha less stringent. Power, again, it's just as it was with the z-tests. We can increase power, which power is the likelihood we'll reject the null, basically, of correctly rejecting the null, or the likelihood that we will find significance if significance is there. We can increase power by increasing the sample size. We can increase the effect size. Now, the effect size basically is, when we think of effect size, it's the m minus mu, the numerator, or the Cohen's d, that absolute effect, the difference between the sample mean and the population mean. We could decrease our error, right? The error. We could decrease the variance in the sample, which would decrease the error. Or we could use a less stringent alpha level, such as 0.05 instead of 0.01 to increase our power. 0.05 is the least stringent that we would ever use. It is the most powerful test criteria that we could potentially use for social behavioral sciences. So hopefully that helps clarify everything for you and breaks down hypothesis testing with the one sample T statistic, which typically you have one sample that you're comparing to a known population mean. If you have questions, please let me know. I encourage you to go back in and watch the little short videos like related to type 1 versus type 2 error, the video related to determining significance. Those videos are very helpful kind of snippets that will help you understand things in a greater detail. Thank you.